Okay, so let's pick up with commands. So we need to think about the syntax and semantics of commands. So far we've only dealt with expressions, which is only a very small part of most programming languages, so imperative ones. So first of all, let's think about the syntax. So the language that we're going to deal with here, the imp version of commands, is going to be conforming to this grammar here. So we have a skip command, which doesn't do anything. I'll come back to that in a minute. We have assignment. So we have an identifier and an arithmetic expression. And again, similarly to the way we handled variables, we're not going to be able to assign to Boolean expressions to a variable, right? There are no Boolean variables, so we've only got a natural number of variables. So this has to be an arithmetic expression. We can have sequencing of commands. So in other words, we can have a command that executes followed by the execution of another command. So that's the traditional sort of semicolon. You'll notice that some of the syntax here is a bit weird because we're going to try and embed this into COC as a notation, and we can't use some of the simple things like semicolons and colons or colon equalses and things because they have a COC meaning. Similarly, the if, we have to use if b because if the if is defined in the library. So if is just a conventional if then else statement. We're not going to support if then by itself statements, but there are some exercises I think that sort of consider what that would mean. But that if its first version is just going to be testing a Boolean condition and then executing either that first command or the second command, depending on what the value of the Boolean is. And there's a while loop, so we can repeatedly execute a command while a Boolean expression is true. So I think all of these will be pretty obvious to you, except maybe the skip. So why do we need a statement that doesn't do anything? So conventionally in PL theory, this is a standard way to sort of avoid some confusions and also avoid having to make the language too big. So for example, if we wanted an if then else, or if we wanted an if then that didn't do anything in the else case, we can just put a skip in this position here. Or if we want to write a simple infinite loop, for example, we could just make the condition, the body of a while loop skip. So the loop will never if it's entered, it will never exit. Another reason for it is that we can also easily define the semantics of something that doesn't do anything and then build up these other constructs rather than having to define individually the semantics of an if with only one branch and so on. Another aspect of this which you may be thinking about is the sequencing. So this says that you can make a command out of two commands. And because this is abstract syntax, we don't really care whether it brackets to the left or to the right or whatever. That's more of an issue for concrete syntax. And for sequencing, it doesn't really matter because the sequencing operator in most programming languages is associative anyway, so we can reorder it, and doesn't really matter whether the bracketing goes to the left or to the right. Okay, so we'll see how these work in a minute. So here's a typical program. This is Factorial, our good imperative favorite program that uses the X and the Y and the Z. Remember, they're just defined to be ID 0, 1, and 2. Right? But it's a bit easier to understand when we use the names. And we can write the program like this, using a loop to just sort of successfully multiply Z's onto Y and subtracting 1 from Z each time until it gets to 0, basically. So that's going to leave the factorial of X in the variable Y, and Z will be 0 and X will be unchanged at the end. Okay, so hopefully the meaning of this little program fragment isn't mysterious. So then we can take this grammar and encode it pretty much like we have done with all the other ones, is in a simple inductive data type. So here's the COM data type, so it goes along with AXP and BXP as to define our language, and there's one constructor for each of the 5 constructs that we have up here. So skip, assignment, sequencing, if and while, each have a constructor, and the syntax of the constructs up here dictates what we have in these different positions. So we have an arithmetic expression on the right hand side of an assignment, we have Boolean expressions in the ifs, and so on. And again, in a real programming language, we probably wouldn't do it quite this way. We would just have one syntactic category for expressions, and then we would use the type system to rule out bad usages of expressions, such as using a Boolean expression where it's not allowed, or using a natural number expression as the condition of a while loop or something. But in this language, we're not focusing on types at this stage, so we're not we're doing it syntactically rather than semantically. Okay, so if we take the COM inductive data type, we can essentially get the notation that we used in our example program by using Cox notation construct, which is basically defining things like a pattern here for assignment and saying, well, that's a thing and that's a thing, so that turns into a CS construct and so on for the other ones. There's a bit of work with parsing so that everything sort of makes sense. So we've got some associativity declarations and some precedence things to make sure things bracket the right way. Don't worry too much about those. But then we can basically take the factorial program that we wrote in the comment before and write it directly as a Coq expression. Okay, so it looks like it's a program, but it's really just building a big tree of the program. Okay, so if I see if we can do this. All right, you see it's actually going to print using the notations as well. Notice that they haven't gone into the detail of trying to define trickier notations for expressions. So everywhere you have an expression, you're just going to see the Boolean constructors or the arithmetic constructors. So it's really only the syntax of the statements that's special. Okay. And if you really want to, you can turn off the notation printing. I think I can do that somewhere in the settings. No, I don't remember where it is. Okay, I'll leave that for you to have a look at. Somewhere, there we go, display notations. So if I go back here and do that again, now we get the full tree form of the construct that we've got. So it's actually quite useful if you're not, if you're new to this sort of stuff, is to make sure that you're convinced that this is the appropriate tree representation for this program using the constructors, because you need to have a good understanding of what the constructors are doing in terms of composing different commands with each other and so on to understand what the proofs are going to do. So that as much as possible, they will use the notations to simplify the presentation, but underneath everything is really just constructs like csec for sequencing and cwhile and cs and so on. So it's important to make sure you understand this. If you leave off the notation printing, then it's going to be a bit easier perhaps to understand what you've got in a proof context, for example. So we'll turn it back on again for now. Okay, so we can use these constructs to define coms, obviously. So here's a few, like x becomes x plus 2, or z becomes x times y, or this one called subtract slowly body is z minus 1, and x is x minus 1. Okay, so these are just expressions like any old expression in Coq. We're just defining a name for something that's a column. Okay, just so happens that these are representing little bits of an imperative program. Okay, similarly we can make subtract slowly. So if we take this body up here, which is just subtracting 1 from z and 1 from x, we can then stick it in a while loop that does while x is not equal to 0, and then subtract slowly body is the bit inside the loop. So what this is doing is saying, well, we want to subtract x from z. And one way to do that is to just count x down to 0, and at the same time subtract 1 each time from z. Every time we subtract 1 from x, we subtract 1 from z as well. So by the time we get to the end, z will be reduced by the amount of x. Okay, so here's a fuller program which says, okay, let's make x3 and z5 and do a subtract slowly. Right? Now notice at this point here, all we're doing is building trees. Right? These are just trees that represent commands, different commands, fragments of programs. It's just fragments being assembled into bigger programs. There's no notion of evaluation yet. And similarly, we can do this loop, which is while true, do nothing. So this is a very trivial form of infinite loop. Okay, so how would we think about evaluation for this? So in the previous stuff, we talked about computational evaluation versus relations that define evaluation. So what happens if we try to do the computational version for this language? So the aim is to take a command and evaluate it. And what do we need for a command to evaluate? Well, it's going to have expressions in it. So we saw before that the expressions, we have to have a state to be able to evaluate an expression. So we need to know what the values of variables are. So we have to have a state as the input. But what does a command evaluate to? Well, it doesn't evaluate to a number or a Boolean, right? Because commands, the thing that distinguishes statements in a imperative programming language from expressions is that expressions have values and commands and statements don't. But we do need to return something, because it might be the case that the command C modifies a state by doing some assignments, some updates to the variables. So the return value of the evaluation of a statement is a state. So it might be that it's the same as ST if there are no updates, but it might be more usefully reflecting the changes to the variables that have happened while we evaluated C. Okay, so how do we write this function? Well, we just have to case out the different possibilities for C, right? Different kinds of commands it could be. So let's try that. So one is, it could be skip. And we said skip's semantics, what skip is supposed to do is nothing. So all it does is return the state that it's given, right? It has no effect on anything. Immediately just gives back the same state that we started with. That's easy. What if we have an assignment of the variable x to the expression a1? Well, if we think about it in a sort of informal notion of what assignment statements do, they evaluate the right-hand side expression, and then they store the value of that expression in the memory associated with x. Okay, so the equivalent in this context is we have to use a-val to evaluate the expression. Remember, we have to give it the current state, because that's going to determine the values of variables inside a1. And then once we have that value, we update the state. So we update st by saying, well, now x maps to the value that was returned by a-val. Okay, so the return value of the evaluation of the command, of an assignment command, is an updated state for the variable it was assigned to, which makes sense. Okay, what about sequencing? So if we have sequencing, we have two commands, and the intended semantics here is that we first evaluate C1 in the state ST, and that's going to give us some new state, which represents the sort of intermediate position here where the semicolons are. And then we have to evaluate C2 in that new state, right? Because we want C2 to see all the values of the variables after C1 is finished. If C1's updated anything, then C2 has to see those updates. And the result that we want to return is the result of whatever the state is after C2 is finished executing. So that's what this code here does. We haven't really seen let, but let basically just says give a name to the value of some expression, right, and then use it in the expression that's after the in. So you can think of let as in Scala it would be a val essentially. So you'd say val st prime equals this, and then you would say, well, this is the thing we actually want to return. So this let is equivalent to that Scala form. Okay, so what do we do? Well, we want to evaluate C1 in the initial state, st, and we can do that by calling this evaluation function recursively. Okay, so we'll get some new state back, which is st prime, and then we want to evaluate C2 in st prime. In other words, the state that resulted from evaluating C1. And again, we just call the function recursively to do that evaluation as well. So there's two sub-evaluations that are sort of chained together by the intermediate state st prime. Okay, what about if? So the sort of informal meaning of if that we want is we want to evaluate the Boolean expression b, and if it's true, we want to then evaluate C1, but if b was false, we want to evaluate C2. So that's easy to do because we can use b val to evaluate the Boolean expression. Again, we have to pass it the current state because it might have some variables in it. And then based on whether that returns true or false, we can choose which one of C1 and C2 to evaluate. And we use the initial state here as well because B can't update the state, so there's no other state. There's no updates happening as a result of the B, so we have to use the initial state. Notice that this is a bit different to, say, in C, where you can have things like updates inside expressions and other things like that. These Boolean expressions here can't change the values of variables. Okay, so this is all okay, so this is going pretty well. The problem is this last case, as you can see by the comment. Fundamentally, we can't do this for while loops because one of the possible outcomes of evaluating a while loop is that it doesn't stop running, right? Infinite loops have to be handled somehow, right? So if we're trying to do it in this fixed point sort of definition, the right answer in some sense is that the evaluation function should never come back when you give it an infinite loop. But in COC, we can't do that, right? We're not allowed to write functions that don't return. All COC functions have to be total, so they have to return a value for every possible input. So in this case, they've just said, well, while loops just are like skip, they don't do anything, which is obviously not the correct meaning. Okay, so this is going to work. They make the point that in a traditional functional programming language, which doesn't have this totality definition, we could actually write something like this, where we say, well, if we evaluate the Boolean expression, and then if that's true, well, if that's false, the loop's finished, so we just give back the state that's currently in play. Otherwise, we evaluate a version of the body, which is this C here, and then the loop again. So this is sort of unrolling the loop one at a time. So each time we evaluate the body once, and then we do the whole thing again, which is going to evaluate the condition again, and so on. And then we start this evaluation of this sequence here in the initial state that we're using for the command evaluation. But the problem is that one is this might never terminate. In other words, if B eval of B always returns true, then we just keep recursing forever, right? Peeling off a version of the command, evaluating it, then going back to the loop. B still true, keep going, right? So if B always returns true, this will just never terminate. And so Coq will reject this definition because it's got to be able to tell that this is going to terminate, and that this error message here is saying the way that it usually does that is by working out that one of these two arguments is getting smaller each time, right? And in this case, this argument here is definitely not smaller than C, right? C in this case is the while loop. Right, sorry, there's two C's here. The C that's the argument to the function is the while loop, and the other C is the body. So this is the body, and this is the original C. So this argument here in the command position is definitely bigger than the one we started with, because it's that one with an extra thing stuck on the front. And so this is not going to work with the Coq, because Coq's not going to work consistently if it allows infinite loops, which is a little bit of the discussion here. So we'll stop there for this part, and we'll come back with a better way, which is, not surprisingly, to use a relation instead of a function to define the evaluation of commands.